All right, so we're going to go ahead and get started. As he said, we're the Vehicle Engineering Senior Design FSAE Autonomous Project. With me here is Bradley Andrews and Brian Fair. I'm Paxton Smith. And so we'll go ahead and get started and get into a little bit of what we did. So to begin with, our objective for this project was to create a drive-by-wire system to control and remotely control three main systems of a Formula SAE vehicle. That would be acceleration, braking, and steering. So our main focuses, we had two main focuses when we were started working on this project, and it was to keep the system as lightweight as possible and try to make sure not to add as much weight with the drive-by-wire components as we could, so we could keep the overall system regulatively about what it would stay if it was a regular vehicle. And then we also wanted to keep the manual driving option too, because with transportation and safety, it would be much better if someone could sit in the vehicle and still control while for testing or just going from one place to another. So why is this project even necessary? Why do we need to do research and try to create a drive-by-wire platform? Well, first off, it's the foundation for an autonomous system. And so by creating this drive-by-wire platform, you can then build upon it to create a completely autonomous system to further this this vehicle and kind of go where the society is pushing and where everything is moving towards. Also, the Formula SAE is starting an autonomous competition, and this could be the potential for Tennessee Tech to get their foot into that, and this could be the platform that kind of starts that group here at Tennessee Tech. So we've had a lot of talk about drive-by-wire. Kind of want to tell you what it is and kind of what's behind it. So as I mentioned previously, it is the platform that an autonomous system is built upon, and it's basically like an RC car. You know, you can control the acceleration, the steering, the braking of that RC car remotely. Like the person does not have to be sitting in the vehicle or connected to the vehicle. There's typically not mechanical connections. Everything's either wire or just remote to be able to control those three main systems of the vehicle. So here's a picture of our test bench. We decided at the initial of this semester, after we done a lot of research last semester, that we were going to mount all of the three systems onto a table so we could more easily work on and adapt to each system, and we wouldn't have to be fiddling with the car. We could just focus on each system and have them represented on this table, and it would also be so much easier to display and to adjust and fine-tune everything as we were moving along in the process.
So a key part for every single system in the design planning was a decision matrix. This tool led us to see each design plan that we came up with and helped us decide which one was the best tool or best design for our system. So design matrix for acceleration, you can see that we had three different designs: electronic throttle body, the pulling the pedal with the linkage system, and then also pulling a wire through electronic actuation. When you received the car, it was drive-by cable. So you saw in the decision matrix that we came out that the electronic throttle body was the highest scoring and was the best design for our system. So these are some of the components that go into it. It's a Bosch 32mm drive-by-wire throttle body, a potentiometer, Arduino Omega, and then an L298 H bridge. So this is a kind of flow chart to show how our acceleration system works. So it starts out over on the left-hand side of receiving a signal that is mounted to the pedal from a potentiometer. And then the potentiometer sends an analog signal to the Arduino. And then the Arduino sends a PWM signal to the H-bridge, which then drives the electronic throttle body. The feedback is coming from the electronic throttle body. It has two TPS sensors that then feeds back to the Arduino to alter the signal to try to come to a steady state quicker. This is a little bit about the potentiometer setup. We did have to make a custom mount for it on the throttle. And then also just a little bit about it. It sends a signal of 0 to 1023 to the Arduino, and then the Arduino can map it out to PWM signal to 0 to 256. So a little bit about the code that we ran and more about the feedback system of the acceleration. So pretty simple. It sends an analog signal, and we just map that down to the PWM signal, the 8 bits of that. And then the feedback is that it sends TPS sensors will send an analog signal back to the Arduino, and we map that down back to 0 to 100. And then we compare the potentiometer signal to the TPS signals, and then pretty much come to a steady state like that by just adding one and then subtracting one. So what can be improved about our system? One of the big things about PWM is that it's not a constant signal. It is a digital signal. So sometimes the butterfly valve will flow to different values, which you'll see kind of in the next video that we're about to show. And then, but to improve on this, you could add a digital to analog converter, which would convert that digital signal to analog. So that should take care of the floating, or you could add some PID control to prevent the floating as well. And here's a video of our acceleration system.
All right, so next up is the braking system. And here's our decision matrix for our braking system. Our first design was our original design. It was a linkage system to pull the brake pedal using a DC motor. Our second design was a pulley system using a series of pulleys and cable to pull the brake pedal. And then our last design was a pneumatic cylinder and cable to pull the brake pedal. After looking at the decision matrix, we decided to go with the pneumatic cylinder. So here are our components for the system. We have a pneumatic linear actuator, electronic controlled air regulator, assorted hoses and fittings, and then an Arduino Mega. Looking at how the system works, the potentiometer sends an analog signal to the Arduino. The Arduino then sends a PWM signal to the electronic regulator. The regulator, based off that PWM signal, either opens or closes, letting air pressure through. Then the pneumatic linear actuator will pull the brake pedal based on the amount of pressure that is given. To do this, we had to do a bit of math to do the electronic regulator to find out how much pressure and stuff we need to get. The regulator operates from 4 milliamps to 20 milliamps. So 4 milliamps being closed and 20 milliamps being fully opened. The regulator that we have operates on current and not voltage, while our Arduino Mega is sending voltage signal. So to solve this, we had to use Ohm's law. Assuming that the resistance was constant throughout, we had to find that 4 milliamps would give us 0.63 volts, while 20 milliamps would give us 1.64 volts. We then had to convert this voltage into a PWM signal. So 32 PWM signal would give us it's actually a typo, 6.63 volts, and an 83 PWM signal would give us 1.64 volts. So we look at what can be improved. The first thing would be adding a feedback sensor, adding a pressure sensor to the linear actuator. This would give us like an idea of how much pressure that the linear actuator is receiving, thus giving like better control over the system. And secondly, just fine tuning the system to get more accurate control of the brakes. So here's our braking demo.
So the last main system of the Formula car would be the steering control. And as you can see, we also did a decision matrix for this too. We had 3 initial choices. 2 of them were pretty close. The other one, as you can see, is not as great as the other 2. But we ultimately decided to go with the DC motor and a ball screw to control the steering for this vehicle. So for the main components, the top picture here will show the back side of the rack. And then the bottom picture shows the front of the rack. And so we have our DC motor, an electronic speed controller, and a ball screw that has a nut with a mount on the rack that controls the movement. And then a rotary encoder, which is not pictured here, that would be on the back of the steering wheel. And then the Arduino Mega. A little bit of breakdown of how everything kind of communicates as you walk through the system. So the encoder on the back of the steering wheel will read a signal of a position and sends that signal to the Arduino, which then sends that signal to the electronic speed controller, and which then sends a signal to the DC motor to move, and which then spins the ball screw and then changes the steering angle of the wheels of the vehicle. So for this system, what kind of can be improved? There's a lot here that could be worked on. It works really well, but when we initially started designing this, we found some ball screws that actually had a kind of clutch or disconnect where whenever there's a force applied the opposite direction or something, they'll kind of break free and they'll slide back and forth. So you can still have that mechanical connection of the steering shaft and not have to worry with no free movement. You can actually still control the vehicle like you would any other vehicle. And this way the driver would have some feedback for the system because currently the encoder doesn't allow any feedback in the steering wheel for the driver if somebody was to get in the vehicle to try and drive it. So also right now, it is an open loop system, so it does not know where the position of the rack is exactly and what the steering angle is. And so what you could do is either you could mount a linear potentiometer onto the rack, and that way you know exactly where the position of the rack is and the steering angle of the wheels, or you could also add limit switches to either end of the rack or both ends of the rack. And that way, once it got to that limit switch, it would know to stop. And that would also prevent some braking that we actually ran into just a little bit, where when we were doing some testing initially, we went a little too far and broke a weld, but that was a simple fix. But if you do add the limit switches, that would definitely improve that design and kind of give it some feedback to knowing where exactly it would be at all times. So here's our video for the steering demonstration. And as you can see in the top left corner, he's controlling that using that potentiometer or encoder. And it's moving it back and forth up and down the rack. So for this system, what would be next? Adding, or for the whole system, what would be next on the table? And what we thought would best would be to add feedback loops, as we previously mentioned, to the steering and the braking systems. Once those feedback loops are in place, you'll have 3 closed loop systems, and you can start fine tuning every system to work together. And once you get it running smoothly and communicating with each system like an actual vehicle would, or an actual person would be in the vehicle, you can start adding the vision system, which is kind of the brain to the whole system. Like, that's what would make it autonomous. So that would be LiDAR, radar, cameras all around the system. And so that would be something you would add as you would move closer into the vehicle, and you would start positioning those things around so that it can actually act on its own and make decisions on its own based on the objects and different things that it sees. We had a lot of help with this project, and so some people we'd like to thank would be Dr. Arman, and Dr. Roberts. They were both our advisors, gave us lots of advice and helped us talk through many different design ideas that we had. Also, Dr. Canfield, he was very helpful in the controls side of things with the Arduino and trying to get some values calculated. So that was really great. And Mark Davis was very good about helping us with all the mechanical components and helping us to actually understand what the FSAE is all about. Since we were working on a formula car, he knows a lot about those, and so he helped us a lot. Some other acknowledgements are students. James Holland is a graduate student. He helped us, and then Andy Bryant, he's on the formula team, and so he helped us out too. All right, is there any questions?